the record button. Yeah. And now we can wait a few minutes until people join. And then I will quickly introduce you and Amira and Ilya, and then we start. Okay, there are still people joining at speed, so let's wait another minute. Okay, I think we can slowly start, and I'm sure there will be a few more people joining. Okay, so good afternoon, everyone. Welcome to this last NITheP colloquium in November. It's not yet the last one in the year. We still have 2 more to come. My name is Francesco Petruccione, and today it is my pleasure to introduce to you Dr. Stefan Woerner from IBM Research in Zurich. Yeah. Stefan is the global lead for quantum applications research and software in the quantum branch of IBM, and he's based in the IBM Research offices in Zurich. He studied applied mathematics at the ETH, and also did his PhD in operations management at the same university. And I guess since then he worked at IBM. I'm not sure, but I'm guessing now. I'm guessing now. Yeah, and his work is focused on the development of quantum algorithms for optimization, simulation, machine learning, in particular with application in the financial sector and supply chain management. Yeah, and today he will speak about prospects of applying quantum computers to solve interesting problems in the financial services sector. Yeah. Before I ask Stefan to share his screen and start his presentation, let me briefly introduce to you the other 2 people that you see on the panel. We have Amira Abbas, who is a PhD student in my group and also working for IBM in Zurich at the same time. Yeah, and Amira kindly agreed, because she also knows Stefan very well, to moderate the question and answer session after and if necessary during the talk. So please make use of the Q&A facility at the bottom of your Zoom screen to ask questions, and we will and Amira will collate them and pose the question to Stefan after the talk. At the top of the screen, you see also Dr. Ilya Sinaisky, and you've seen him probably many times. And Ilya acts as co-host of this event, just in case my internet connection dies or something, yeah, so that the seminar can go on. Stefan, we are all really very happy that you agreed to give us this talk this afternoon, and you're welcome to start sharing your screen and get ready to start your presentation. Thank you very much.
Thank you very much, Francesco, for the introduction. So, and the invitation to present. So let me share the screen. Can you see the presentation?
Yes, perfectly. Thank you very much.
Okay, great. So yeah, I'd like to give you an overview of some of the research we did in the last years of applying quantum computing to the financial service sector. Of course, these algorithms and applications I present are more generic, but we looked into particular applications here to showcase the capabilities of what we think can be done eventually once the quantum hardware grows to the right scale. So I structured this into two parts. The first part is a brief introduction to quantum computing in general, and then I'll dive into applications in finance. All right, so let's start really with the basics. What's the basic unit of information? Classically, that's the bit, which is either 0 or 1. And in quantum computing, we have the quantum bit or qubit, which can also be 0 or 1, but it can actually take any state that's on the surface of the so-called Bloch sphere. And you see here at the North Pole, you have the 0 state, at the South Pole, you have the 1 state. But it can also be in what we call a superposition of the two states. So for example, on the equator, there would be a equal superposition where it's the same way between 0 and 1. Now, a bit more formally, we have these two basis states, 0 and 1, that we can identify with a standard basis in linear algebra. See here these two basis vectors. And then the state of a qubit is a linear combination of the two, as what you see here. And the weights are complex numbers. So you can write this down as a vector with the requirement that the weights are normalized in that way. And then the last property here of a single qubit is that if we measure that, so if you really want to look at the state, we cannot directly measure the state, but we will see a 0 or a 1 with a certain probability. And this is now the weights here. So alpha squared is the probability of measuring 0. Beta squared is the probability of measuring 1. So the closer we are to the 0 on this Bloch sphere, the higher the probability that actually we see a 0. And same for 1. The closer we are at 1, the higher the probability to see a 1. If we now have 2 bits, then 2 bits are in exactly 1 out of these 4 basis states. Now, if we have 2 qubits, they can take the same state. So they can be in those 4 basis states, but they can also be in superpositions of these 4. And they can also be in a state where the 2 qubits are kind of correlated, and that's what we call entanglement. Again, a bit more formally, first we have here the so-called Bell state. That's a superposition of 0, 0 and 1, 1. This is very special because this state does not exist classically. Because here, the state of the 2 qubits are perfectly correlated. If we only measure the first qubit and we would see a 0, then we would know that the second state is also a 0. And likewise, if we would see a 1, then we would know the second qubit is also in state 1. So we have this perfect correlation. And this is in the quantum computing context what we call entanglement. And there can also be non-entangled states like this one at the bottom, where we have all 4 possible basis states with the same weight. And this is what we call the equal superposition state. And here, if we would only measure 1 qubit and we would see this in the 0 state, for example, then we still do not know anything about the second qubit. So these are the 2 extremes in a way. We can also have things in between. Now, if it would only be for superposition and entanglement, then we could actually simulate quantum computers classically. But there's one more effect, and I'll get to that on the next slide. But the key difference between quantum and classical computing is that these amplitudes can be negative. And I'll illustrate in a bit what that means. And this allows us to leverage interference. You may know interference from sound or from water, like if waves add up or cancel out, so we can have constructive and destructive interference. And I'd like to briefly illustrate what this means from a quantum computing point of view.
Stefan,
yeah.
Just before you go on, somebody has asked, why is the entangled state not possible classically? So what makes it different, an entangled state?
So this is an effect between two, if you want, between 2 particles that kind of takes place immediately. Like you can entangle 2 qubits and then send them to to the other end of the globe. And still, if you would measure the one, you would immediately know the state of the other. So it's like this, this correlation, which is really kind of not local anymore. And this effect of this correlation that can happen even at 2 different places at the same time, this is something that's not possible.
Perfect, thank you.
So about interference. So here we have an example with 3 qubits. So there are 8 possible basis states, and we put them into equal superposition. So here, this is illustrating the amplitudes of the different basis states, and this dashed line indicates the average over all 8 amplitudes. And then we mark one particular state. And depending on the application, we do not need to know this explicitly. That might be something we are looking for, and we can somehow write this as a function or something like that. And what we can then do is we can actually multiply this by -1. So this is what we've seen before, that these amplitudes can have a sign. And if we now look at the average overall, this reduced a little bit because one of them is now negative. And now there's an operation which is called reflection around the mean. So we can actually just reflect every individual amplitude around the mean of all the amplitudes. And if we look what happens, then this is the effect. And what you see now is that the one amplitude that we've flagged at the beginning, this is amplified. And this is actually what's happening in most of the quantum algorithms, that we're kind of amplifying the states out of this large set of states that's possible that we are really interested in. And this effect, this possibility to amplify amplitudes, to leverage interference, is really what makes quantum computing different from classical computing. If it would not be for these negative amplitudes, we could use stochastic simulation or stochastic classical algorithms to simulate quantum computing. And this simple algorithm that I illustrated here, this is actually Grover search, and this is one of the most famous algorithms, and you might have heard about that. All right. Now, very briefly, we talked about the single qubit and how to represent the state of a single qubit, and there are 2 basis states, so we can represent that with 2 complex numbers. If it's 2 qubits, there are 4 basis states, and so on. It's 8. It grows exponentially with the number of qubits. So if it's n qubits, it's 2 to the n quantum states. And just to put this somewhat into relation, if we think about a system with 275 qubits, then the number of basis states actually exceeds the number of atoms in the observable universe. And if you think about what this means, if you would like to build a classical computer that can simulate systems of that size, then this presents a rather fundamental limitation to do so. So that's, on the one hand side, this is really nice because we get this large compute space, but on the other side, we also have to be very careful with that, because we somehow need to efficiently load data or load the problem we want to solve into this very large compute space. And efficient in this case means that it's kind of polynomial in the number of qubits. So if we would just want load a data set that's very large into this quantum computer, then this is can often happen that this impedes really the quantum advantage, because loading the data into the quantum computer can be as expensive as solving the whole problem just classically. So here we have to be really careful, and I get back to that in a bit. We always have to analyze quantum algorithms or applications end to end. So loading the data, which can be a bottleneck, and extracting the result, which can be another bottleneck. So we have to find a way to make this efficient and then leverage this exponentially large compute space in the middle. Okay, how can we actually program a quantum computer? So classically, there are these gates, and or not, and so on. And this is kind of the fundamental level at which we program a classical computer. Of course, we have higher level languages available these days, but that's what it can be reduced to. On quantum computers, we also have gates. It's a different set of gates, but in the end, it works relatively similar to that. So we apply single qubit gates to modify the state of individual qubits. We have 2 qubit gates to entangle 2 qubits, and with a set of single qubit gates, and actually this one 2 qubit gate, this is a controlled NOT gate. This is already universal. So with this set of gates, we can represent all possible quantum circuits. Similar to classically, you can represent everything with only NAND gates. Here you can have arbitrary single qubit gates plus 1 2-qubit gate, and this is all you actually need. Now, we actually do have a graphical interface that you can draw these circuits and simulate them or run them on the real hardware, and you can make an account in the IBM Quantum experience to test this yourself. But we also have Kiskit, which is an open source Python framework to program quantum computers to simulate these quantum circuits and also to access the real hardware. And in Kiskit, you also have already a couple of quantum algorithms directly implemented, and there are many tutorials that show how you can use them. I also briefly get back to that in later. All right, so this is actually how a quantum computer looks like. You have here a chip. This is with 8 qubits. Here the squares are the individual qubits, and these lines in between are microwave resonators to connect them or to read them out and so on. This you can barely see this with your eye. So it's to give you an idea about how large this is. Then this is mounted on a circuit board, which is then placed here at the bottom of this fridge. This is a dilution refrigerator that cools down to 15 millikelvin. So this is like very close to the absolute zero temperature. And this already gives you an idea that these things are rather fragile. So these qubits need to be really shielded and cooled down and protected from radiation. Otherwise, they lose their state. And it's even more complex to that. So there are quite a lot of possible effects that can destroy the state of the qubit or that make your gates imperfect. So there's errors, noise, and things like that. And these physical qubits are therefore really not so easy to operate with or do meaningful calculations with. And therefore, the number of physical qubits is also not a very good indicator of the computational power of a quantum computer. And therefore, we introduced the quantum volume. And the quantum volume is a benchmark, a single number benchmark that takes all of these things into account and assigns a number to a particular quantum device. And this helps to really compare the computational power of quantum computers and to track how this power increases over time. And if we have a large enough quantum computer with sufficient physical qubits with the right with low enough errors, then we can actually apply error correcting schemes to build logical qubits. And these logical qubits are then have an exponentially suppressed error. So we can think of them almost as error free. And today estimates are that we likely require around a few hundred to 2,000 physical qubits to build a logical qubit. And then of course we want to have many logical qubits to do our computations. And this is then what we call fault tolerant quantum computing. And I'll get back to that when discussing applications, because some of the applications we hope will already profit from noisy quantum computers, so using physical qubits, and some applications will require fault-tolerant quantum computing, so where we then need logical qubits. And because of this overhead of a few hundred to 1,000 from physical qubits to logical qubits, a fault-tolerant quantum computer is also further out in the future. So these are more long-term applications. Now, recently we released the IBM roadmap on how we want to scale our quantum hardware. And here you see in 2019, released this 27 qubit chip. This year we released the 65 qubit chip. Then next year we plan to release 127, then 433 qubits. And then in 2023, we plan to exceed the 1,000 qubits. And this will then also be a new generation of quantum devices that's built in a way where we think that it can be scaled also then beyond the 1,000, really to in the longer run to millions of qubits. And this is also the generation of devices where we think that we can then start to really study fault-tolerant quantum computing. Then first at a smaller scale again, so with 1,000 qubits, these are physical qubits. we have to see how many logical qubits we can make out of that. But then as this scales further, we think that we can then really leverage these devices also for fault-tolerant quantum computing and achieve an advantage here. Okay. So much about the brief introduction to quantum computing. Now I'd like to dive into applications in finance. And this next part is divided in 3 areas. The first is on machine learning, second on optimization, and the last on simulation. So let's start with machine learning. And here we have seen this before. This is particularly important in machine learning. So it's difficult to load large data sets into a quantum computer. And therefore, we will have to see whether quantum computing can really help for large data, for big data applications. It might in the longer term, but near-term applications, I'm rather sure that here the goal will not be to speed up calculations for large data sets, but rather improve accuracy for moderate sized data sets or things like that. And we'll see a few applications in the following. And most of this section is focused on binary classification. So the problem that we are looking at is that given a labeled data set, we want to train a classifier such that given a new data point, we can easily decide whether it's in the one class or in the other class. So in this example, whether it's orange or blue. If we have a classifier that can do this reliably, then there are plenty of applications. And here I listed a few relevant to the financial service sector, like fraud detection, credit risk rating, or customer segmentation. One way to solve this problem classically is a support vector machine. And a support vector machine essentially computes this white hyperplane here in the middle, which separates the 2 classes in the best possible way. And if you have this hyperplane and you get a new data point, you can very easily tell whether it's left or right of this hyperplane, so whether it's blue or orange. The problem arises if the data is not linearly separable anymore. And here's an example, and real world data is rarely linearly separable. And the question is, how can we solve this? And colleagues of ours from IBM Research in Yorktown proposed to actually apply a quantum feature map to that. So here you see a classical feature map. This is just a quadratic function. And you see suddenly this data gets linearly separable again. But with a quantum feature map, you could take this data and map it to an exponentially higher dimensional space. And there you may be able to actually achieve a higher accuracy. And this can be used, for example, in quantum neural networks. And this is now a illustration of a 5-qubit circuit where we first apply this quantum feature map. And this is a parameterized quantum circuit that takes a single data point as input and then prepares a quantum state that kind of corresponds to this data point. And if we think of a data point that has a dimension which is order of the number of qubits, so in this example 5, then we map this to a 2 to the 5, so 32-dimensional feature space. And the dimension of this feature space really grows exponentially with the number of qubits, and this can help to improve the accuracy of the classification. Then in this example here, we have this orange box. This is again a parameterized circuit, but this is now really a circuit that we train. So these angles theta are trained in a classical training loop. And you can think of that as the layers of a classical neural network. And then we measure this. For every qubit, we get a 0 or 1. And so we get a bit string out. And then we need to assign a value to this bit string. So in our classification example, it's one of the 2 classes, blue or orange. And since these measurements can be stochastic, we don't do this just once, but we do this a couple of times so that we can assign this value with a certain confidence, or if it's not a classification, but a regression task, we can use the average, for example, to also represent continuous numbers. Now, this whole idea of a quantum feature map has been introduced and discussed in different settings last year in this paper here, where it has also been demonstrated on a real quantum device on this artificial data set that you see illustrated here at the bottom left, where it could be shown that this can really work very well. And actually, just a side comment, in a very recent paper by our colleagues from Yorktown, they could show for an artificial problem that such an approach can really lead to an exponential speed up for compared to classical classification tasks. Now, this proof is for an artificial problem, so it's just to demonstrate that this can happen. But there's still the open question how powerful these quantum models are in general for applications that arise, for example, in finance. And we looked into this problem recently, and also Amira was involved here, and we found some first answer to this question. And before you can answer this question, you need to answer the question of how to measure actually the power of such a model. And here we introduced and looked into the effective dimension. I don't want to introduce this here formally, but the effective dimension essentially covers how many of the parameters that define a model really contribute to its power. And it also relates this to the available data, to the number of data points that you have to actually train your model. And you see here that we looked into classical neural networks and also different types of quantum neural networks, and we analyzed their effective dimension. And here we actually tested a large set of classical neural networks, and this is the best one that you see here. And you also see that the quantum neural network really has a significantly higher effective dimension than the classical one. And this indicates that quantum neural networks with the same number of parameters as classical neural networks can really perform significantly better. To also illustrate this on a practical task, we trained these different networks on a simple problem. I think this was a subset of the IRIS data set. And you see here the number of training iterations and the resulting loss function. And you see the red, blue, and green line are classical simulations, the red of a classical neural network and the blue and the green of quantum models. And then the black line is actually the training of a real quantum device on this task. And you see that the green line decays significantly faster than the other two, and the black line nicely follows this behavior. So quantum neural networks have higher effective dimension, but they can also be trained to a lower loss faster. So this is pretty nice. Then there was one other insight that we found in this paper, which was actually that depending on the choice of your feature map, quantum neural networks can also avoid what it's called barren plateaus. And barren plateaus is something, or the name is used particularly in quantum machine learning. Classically, it's the problem of diminishing gradients. And this can also happen for quantum neural networks. And here we could show that these quantum neural networks with good feature maps seem actually to be kind of robust to this problem.
Sorry, Stefan, two participants are just asking, what is the easy quantum model? What does that mean?
That's a good question. So I mentioned that good feature maps can avoid barren plateaus. There are feature maps that actually could be simulated classically. So it's kind of a poor choice for a feature map. And there are feature maps which are conjectured to be very difficult to simulate classically. And here we picked two, one easy, where we were hoping that this does not work well, and one difficult to simulate classically feature map where we were hoping that we kind of see a separation between the two. And that's exactly what you see here. So the easy quantum model is using a feature map that we conjectured is a poor choice because it can be easily simulated classically, and another one that is where we think that it's difficult to simulate that classically, and that's the difference you see here. All right, so I want to briefly mention one other type of quantum machine learning model, or quantum neural network if you want. That's quantum Boltzmann machines. So this is motivated by classical Boltzmann machines, but extends this concept to quantum machine learning, And here I won't go in detail how this exactly works. I mainly want to touch here on the application that we looked into. But very briefly, in a quantum Boltzmann machine, the information is actually not encoded in a quantum state or in a quantum circuit. It's encoded in a Hamiltonian, in a parameterized Hamiltonian. And then for this operator, we construct the Gibbs state, and so a thermodynamic state based on this operator. And then we measure from this resulting quantum state, and we use these measurements, these statistics, either for some classification or some generation task, for example. And then we use the results from that to update actually this parameterized Hamiltonian. Now, this is another quantum machine learning model, but that can be applied similarly to what we've seen before. And we introduced here a variant of quantum Boltzmann machines that should be applicable on near-term quantum computers and noisy quantum computers. And we applied this to a credit card fraud. More precisely, we actually used the synthetic toy credit card fraud data. And colleagues of ours in IBM Research in Yorktown do research on synthesizing credit card fraud data to actually train large, to have larger training data sets for classical machine learning. That was the intention. And there's also a publication on how they do this. And we asked them to generate a smaller credit card fraud data set for us with 3 features plus the label and 500 training data points and 250 test data points. And then we applied different models on that. And you see here a bunch of classical machine learning models and our variational quantum Boltzmann machine. And here you see these different indicators, and it can be seen that the variational quantum Boltzmann machine really performed best over all of these other models. And this is an illustration of what kind of quantum advantage we hope to see with these near-term quantum computers over classical models. And in credit card fraud, if we could reduce the false positives, and this is what this Boltzmann machine achieves here in this simple test, this can have a huge impact, saving money, increasing customer satisfaction, and things like that. So let me summarize for the machine learning part. When do we expect a quantum advantage? And this is a very difficult question, and I will not be able to give a conclusive answer here, but I can give an estimate and put things into perspective. So we have these quantum support vector machines, quantum neural networks, variational quantum Boltzmann machines that are near-term compatible. So we hope that with a quantum computer without this error correction, we can apply these algorithms to realistic problems once the number of qubits and the quality of the qubits reach a certain point. And if we compare that classically simulating quantum circuits with more than 50 qubits becomes very difficult, even on very large systems, then we can kind of conclude or expect that with order of 100 qubits of a sufficient quality, we could see a first quantum advantage, because we can do things that classically are difficult. Will this really be an advantage in machine learning? Yeah, maybe. It's hard to tell right now, but there are good indications that this might be an application that profits rather early from quantum computing, and also from near-term noisy quantum computing. All right, now let's talk about the second application area, that's optimization. And here we mainly focus on combinatorial optimization, or more precisely, quadratic unconstrained binary optimization. And this already tells you what kind of optimization problems we are focusing on. So we are minimizing a quadratic objective function without constraints over a set of binary variables. And that may sound a little bit restrictive, but this class of problems still covers many interesting problems like portfolio optimization or portfolio management, as illustrated here, where we want to, for a given risk level, find the maximum expected return. And I briefly get back to that in a moment. So here we usually want to find this efficient frontier, the optimal risk-return trade-off. Other applications are optimal feature selection, where we have a given data set and we want to find for a particular machine learning task the best set of subset of features. That can also, or variants of that problem can also be formulated as a QUBO. And other problems like Max car traveling salesman problem, etc., they all also fall into this class of problems. Okay, now for this class, we mainly look into near-term quantum optimization heuristics. And here I want to emphasize two words. The one is near-term. So we think that these approaches are applicable also to noisy hardware, or at least most of them. And the other word is heuristics. So although we think they can lead to an advantage, we do not have really a theory yet. So we really, from what we know today, we need to demonstrate empirically, once the hardware is large enough, that this can lead to a quantum advantage, or for which problems it can lead to a quantum advantage. Now, these algorithms usually follow a pattern similar to the training of a quantum machine learning model, where we have a classical computer that controls some parameters. These parameters define what's actually happening on the quantum computer. And then we measure the results in the quantum computer and we feed them back to the classical computer to update the parameters. And so we have this feedback loop that helps us to train the quantum computer towards a good or an optimal solution. And this is a brief example. So here we have 3 qubits, and this corresponds to 3 binary variables. So we have a one-to-one relationship usually. We have these single qubit rotations, which are parameterized. So these are 3 parameters that we train in this loop. Then we have here a couple of 2 qubit gates that entangle the qubits, and then another layer of single qubit gates that are parameterized. And then we can repeat this a couple of times. Due to the noise in the system, we cannot repeat this as often as we want. So we have to find the right depth, so that this is still feasible given the errors and the noise that are present. And then we measure at the end, and then we get again a bit for every qubit. And this indicates then whether our binary variable is 0 or 1. So every measurement at the end gives us a possible solution to the problem we are interested in. Now, one crucial question is, how should we actually choose this circuit for a particular problem? And without going into much detail here, there is the so-called quantum approximate optimization algorithm, where this circuit is constructed really from the problem that's given. So you construct a problem-specific parameterized circuit, and in this particular case, this is motivated by the Adiabatic Theorem, and we know that if we would repeat these layers often enough, we would converge to the optimal solution. But since we cannot, and we have to truncate, it is still a heuristic. We tested these heuristics on portfolio optimization, and here this is the illustration of the problem we actually looked at. So this was a 5-asset problem with here the expected returns, the covariances of the returns, and then you see here the resulting efficient frontier for different budget levels. And this results from a real quantum computer actually. So what we could show so far is that these methods at this small scale work, but it's still very difficult to answer the question about what quantum advantage to expect. And here I'd like to briefly talk about a very recent research result where we could show how to warm start quantum optimization. So what we do here is we leverage the best available classical solvers for a problem, and we use the solution of them as an input to a quantum algorithm. So this is illustrated here at the right-hand side for a quadratic programming relaxation. So this first picture shows a QUBO with two variables. And then if we, instead of forcing variables to take 0 or 1 as values, allow also continuous values between 0 and 1, then we get this continuous relaxation. And we can usually assume that this is convex in our case. And this can be easily solved classically. This gives us then a continuous solution. We can use this continuous solution to construct a quantum circuit that actually starts off at this continuous solution, and then we can use this to derive a solution for the QUBO. Now, quadratic programming relaxation is not the strongest relaxations that you can use, and we also show how this can be done with semi-definite programming relaxations. And here, those are often optimal classically. So it's known that you cannot get any better efficient algorithm classically that achieves the same level of approximation. So we tested this for the max-cut problem. And here we warm started with the Gurmans-Williamson SDP relaxation. And this is known to, or this is the best known classical relaxation for max-cut. And here I won't go too much into the results here. I'd like to just briefly explain the main finding. We tested here 4 different algorithms: the classical Gurmans-Williamson, a standard recursive QAOA, this is this quantum approximate optimization algorithm, our warm started variant of that, and then also a recursive classical Gurmans-Williamson heuristic. And these are four sets of experiments, each with 100 random graphs. The top row is with 20 nodes, and the bottom row is graphs with 30 nodes. And the x-axis is the approximation ratio. That means that 100% means we really found the optimum. And the smaller this approximation ratio, the worse the actual solution. And what you nicely see here is that for all 4 problems, our warm started optimization algorithm actually outperformed the others. And the most difficult problem class is the bottom right here. And there you see that the difference between the different algorithms gets larger, and the warm started optimization actually really performed significantly better than the rest. Now, why does it make sense to warm start quantum optimization? This is now a little bit of complexity theoretical discussion. First, it's not expected that quantum computers can solve NP hard problems in polynomial time. So this is unproven, but this is a widely accepted conjecture that NP hard problems also won't be solvable in polynomial time on a quantum computer. In general, we only expect a quadratic speed up for NP hard problems. However, we may be able to actually get better approximations, so efficient approximations like the Gurman-Williamson approximation, where we have a certain approximation ratio guarantee. And I'd like to again discuss this on the example of max-cut. So if we look at Gurman-Williamson, this provably achieves an 88% approximation ratio on average. So we achieve 88% or at least 88% of the optimum. And in complexity theory, there's the unique games conjecture. And if this holds, then Gurman-Williamson is optimal. Then there cannot be a better classical approximation. And if the unique games conjecture would not hold, and if you would only assume that P is not equal to NP, then the upper bound for this approximation ratio would actually go up to 94%. So this from 88 under the unique games conjecture to 94. And now it's known that for quantum computers, the unique games conjecture is false. And let me discuss what this means on this figure on the right-hand side here. So classically, under the unique games conjecture, we can achieve this green area for max cut up to 88% approximation ratio. In contrast, the red area from 94 to 100% this is not reachable with any efficient algorithm, whether classical or quantum, unless P is equal to NP. And then there's this orange area in the middle, which is unlikely to be accessible classically, but can still be reached with a quantum computer. And with our warm starting of quantum algorithms, we actually start exactly at the boundary, and then we can improve upon it. So the theory is just at the very beginning. We do not have any proof yet that we can really go into this orange area, but this is I think a very promising area of research, how quantum computing can, also for near-term quantum computers, can help in combinatorial optimization. Now let's quickly also talk about when to expect the quantum advantage. So I mentioned this before. Usually we have a one-to-one relationship between binary variables and the number of qubits. And if you look at classical benchmarking libraries, then usually up to 1,000 discrete variables problems tend to be easy, meaning you can solve them in less than an hour on a desktop computer. Then around 10,000, they tend to be hard. That means they have been solved, but possibly in longer time and on larger hardware. And if you go to 100,000, then they often are open, so they haven't been solved to optimality. This is a bit simplification, but it gives you some orders of magnitude. And that also means that due to this one-to-one relationship, that we can expect a quantum advantage here, likely if we reach a problem size of 1,000 to 10,000 variables. So this is likely the scale where we hope to see a quantum advantage. And particularly in finance, even if it's only a small improvement, this can have a huge impact because there's often a large leverage involved. To conclude on this optimization section, I'd like to briefly mention the Kiskit optimization module. So I mentioned Kiskit before. This is our Python framework to program quantum computers. And in Kiskit, there's the optimization module, which allows high-level modeling of optimization problems with classically established best practices like DO-CPLEX. And then you have a bunch of quantum optimization algorithms, and they all have the same interface. So you can directly take this problem and pass it to different algorithms. And all the translation to quantum oracles, to Ising Hamiltonians, to variational forms, or circuits. So all this translation necessary is done automatically. And you can then also directly run this on the real quantum hardware. We also have some classical solvers that can be used to test, validate, and benchmark these algorithms. And all of this is built in a very modular way so that it's not only easy to use from a high level, but that it's also very useful for really quantum optimization research, because you can replace every single building block by your own implementation and see how this performs, how this improves things. Okay, now the last application area, simulation. And let me briefly explain the problem that we are looking into here. So suppose we have some distribution which can describe a loss or a profit, for example. Then we may be interested in estimating different properties of this distribution, for example, the expected value. That's if we talk about pricing, financial derivatives, or risk metrics like the value at risk or the conditional value at risk, so these tail probabilities of the distribution. And the most generic approach to estimate these things classically is Monte Carlo simulation. And that essentially means you sample from this distribution, and then you do some statistics or you count. So you throw a dice many times, and then you count how often a certain event took place. And although that's very generic, you require many samples to get a decent estimation. So the estimation error scales relatively slowly. And here quantum computing can achieve a quadratic speedup. That means that where you need millions of samples classically, you only need a few thousand samples using a quantum computer. And this is illustrated here at the bottom. This is from an experiment that we run on real hardware, where you see the number of samples at the x-axis and the resulting estimation error on the y-axis. And you see the error for the classical Monte Carlo and the quantum algorithm, which quickly surpasses. And up to this point, So the solid part is on a real quantum computer, and the dashed line is from a classical simulation. Now, I'd like to briefly sketch why we get this quadratic speedup, or what's the intuition behind. And let's suppose we have a simple problem like that. This is kind of an unfair coin where we get a 1 with 30% probability and a 0 with 70% probability. And our goal is to estimate the expected value of that, which is same or equal to the probability of measuring a 1. And in the end, we'll reduce every problem to that setting. It doesn't matter whether this is a complex financial derivative, we'll always reduce this to this setting. Then we can map this to a qubit. And here you have again the Bloch sphere. And we assume that we have an operator A. And this is actually the encoding of the problem, such that it maps the qubit to a state such that the probability of measuring a 1 corresponds to what we expect here. And we do not necessarily need to know this explicitly. So for complex problems, you can also construct that so that we don't know this upfront. And now, since in quantum computing, we are usually talking about rotations on this Bloch sphere, we can interpret this probability also as an angle. And here we write this probability of measuring a 1 as the sine square of an angle theta. And now, one thing we could do is we could just measure directly. That would actually be equivalent to Monte Carlo simulation. Or what we can do is we can construct another operator Q. And this is very similar to what we've seen at the very beginning with this interference and reflection around the mean. And I don't want to go into detail of Q here, but Q is an operator that we know how to construct given A, so given the problem. And if we apply this operator Q k times, then what's happening is that we actually measure this probability 1, or that we measure 1 with the probability that's now given by sine square of multiples of this angle theta. And now it's quite nice, because if we use this in the right way, so if we don't apply Q an arbitrary number of times, but for example 2 to the k times, then in a way this allows us to estimate the kth bit of this angle theta. And if we think about what this means, if we add 1 more bit to our estimate, this means that we reduce the estimation error by a factor of 2. So the error is multiplied by 1/2. And this happens at the cost of, since we apply Q 2 to the k times, the cost to do so is also 2 to the k. So we achieve an error of 2 to the minus k, because we get 1 bit at a time, and the cost is 2 to the k. And this is actually already the quadratic speedup, because if we would use 2 to the k samples classically in Monte Carlo simulation, we would get an error of square root of 2 to the minus k. And so this is the difference, that here we can construct these derived problems that allow us to estimate bit by bit, essentially. This is the basic algorithm behind that, and it's called quantum amplitude estimation. And here you see these operators A and Q, and here these different powers of Q, and here you actually do the simulation at the bottom, and you extract 1 bit at a time through these controls. So you're kind of entangling your simulation with this results register, and in the end you can measure the result. A bit simplified, this bottom part is the actual simulation, and this red box is only to extract the result. And this canonical quantum amplitude estimation has been published in the year 2000. Now, there was quite some development here in the last year. First, there was an algorithm by our colleagues in Tokyo who could show that you can actually drop this red part and only focus on the green box. So you can simplify the circuits. This algorithm still achieves a very good performance, but we didn't have a rigorous proof yet about the error bound, actually. Then a bit later in this last year, there was another paper which again could show how to simplify the circuits, and they had a rigorous theory, but this involves large constants. So this is actually, from a theoretical point of view, a very interesting contribution, but not practical yet. And then at the end of last year, we introduced yet another variant of this algorithm, that could actually achieve the simplified circuits, a good performance, and the rigorous theory. And we implemented all of these algorithms and compared them. And here again, you have the number of samples on the x-axis and the estimation error on the y-axis. And in blue, you have the Monte Carlo simulation, the classical one as reference. And then you see the different quantum algorithms where you have the first one with the rigorous theory in red, the canonical one in this lighter blue, the first one that simplified the circuits in orange, and then the last one, the iterative quantum amplitude estimation in green, which is the most efficient variant to date. So we tested this for different applications, and one was option pricing, where we actually showed how you can translate different option contracts into quantum circuits. And we also looked into how you can load stochastic processes like stochastic volatility models and things like that, that are modeling the underlyings for this stochastic for this financial derivatives. And so this is one possible application, option pricing. We also looked into credit risk analysis, where we could show how you can model large credit portfolios and make them accessible to this amplitude estimation. And here we could also show that under the assumptions that we make about error correction today, that if we would have a large enough quantum computer, that we could actually solve large portfolios with like million assets in essentially a near real time. All right, so last, when do we expect a quantum advantage for this application area? So first, there have been significant improvements in the algorithms that reduce the requirements on real hardware. However, the circuits are still very deep that we get out. And therefore, we think that this requires error correction. And to model something interesting, we likely need a few thousand logical qubits. And due to this overhead of error correction, we likely require, I don't know, around 1 million physical qubits. So it's certainly not a near-term application. However, this amplitude estimation algorithm is extremely universal. So as soon as we have the hardware that can run this, there will be tons of applications that can profit from it. And to summarize now everything, we recently published a review paper on quantum finance that goes into more detail for all the areas that I mentioned. So there's a discussion on machine learning, optimization, and simulation. So if you're interested in more details, that's a good starting point. And with that, thank you very much for your attention. And I'm very happy to take your questions now.
Yeah, Stefan, thank you very much for an excellent talk and a great overview of what is technically possible with quantum computers in the financial world today. And now I will ask Amira to please guide us through the question and answer session. Amira,
Yes,
please,
sure.
over to you.
There are quite a few questions, so I tried to answer a little bit of them just in the interest of time, but just to summarize, one of the main themes that came up a bit was about what data sets can quantum machine learning models actually handle. So what size, how large are they, and particularly the credit data that you mentioned, which data set was this?
The credit data for the credit risk analysis?
Yes, exactly.
Okay, so I think these are two questions. For the credit risk analysis, we just made up a data set. We followed this Gaussian conditional independence model, which is from the literature, and we here it doesn't really matter what data it is. This data requires a set of parameters. So for every asset, you need a base default probability and a sensitivity to some global latent variable, and we were just assuming that this is given, and then we estimated the runtime. But the algorithm is not depending on the concrete data here. For the machine learning models in general, there's kind of a rule of thumb that the number of features that we load to these models should, let me quickly jump to the slide, that the number of features that we load here should not, or should be of the order of the number of qubits that we use. because if the number of features is significantly larger, then at some point there's likely no point in using a quantum computer, because the feature space that you map into is not significantly larger anymore than your feature space you start with. Like an extreme case with this 5 qubits, if you would map a 32-dimensional classical data point into this quantum state, you would map from a 32-dimensional space to another 32-dimensional space. So that's kind of a rule of thumb, that the order of the number of features should be similar to the number of qubits. Now, the number of data points is not really limited here, because we load the data points one by one, or if you use a kernel-based message, you load pairs of data points. And there you just repeat classically, essentially.
Okay, cool. And then a more general question was asked about what are the properties of applications that can benefit from noisy physical qubits compared to those that require fault-tolerant quantum computing?
That's a good question, a very difficult question. I can, I mean, we have these examples for classification, maybe also regression, where we can use these quantum neural networks, and we have algorithms for combinatorial optimization. So I think these are two classes where we have candidates that may run on noisy hardware. One thing that's, I think, a common pattern is that these algorithms that run on noisy hardware are usually heuristics. So we have to demonstrate empirically the advantage once the hardware is available at scale. This proving the performance for these noisy algorithms is very difficult. And I think this warm starting of optimization, this is for optimization, to my knowledge, the most promising approach, but also this is at the very beginning.
Okay, I see we're out of time, but Stefan, do you mind taking one or two more questions? Do you have time for
No, that's fine. Yeah, sure.
Okay, cool, perfect. So just, I think one that will be quite quick. Somebody asked, do classical QUBO solvers running on GPUs compete with current near-term QPUs?
Classical QUBO solvers by far outperform current quantum devices. And I think the classical QUBO solvers, unless you reach, let's say this 1,000 variables, classical QUBO solvers can handle these problems very well. So I think once we reach this 1,000 to 10,000, then things start to change. But until that point, I don't really expect too big of an advantage using quantum computing.
Okay, cool. And then you mentioned briefly the Adiabatic Theorem. Can you elaborate a little bit more how this comes into play?
Mm-hmm. That was here. So in the Adiabatic Theorem, what we actually do is we construct a very easy optimization problem where we know the optimal solution, and we will prepare this optimal solution. And what we can do now is we can drive the system from like we apply a time-dependent Schrödinger equation essentially, or we trotterize that, and we drive the system from the problem we started with, which was easy and where we start in the optimal solution, to the problem that we are really interested in. And by doing this slowly enough, we always stay in the optimal solution of all the intermediate problems. So in a way, we change our problem from an easy one to the one we are actually interested in very slowly. And the Adiabatic Theorem guarantees that if the initial state, which is the solution to the easy problem, has some overlap with the optimal solution to the problem we are really interested in, then we'll actually reach that optimal solution in the end. And if in this quantum approximate optimization algorithm, we would do enough layers here, we would repeat this often enough, and we would make the circuit long enough, then this would translate to actually slowly transition from an easy problem to the problem of interest and staying in the optimal solution of all the intermediate problems.
Okay, cool. I think, so there are many other questions, but I think I would suggest that people just write to Stefan if you have any pressing matters. But also a lot of people have asked for the references slide, if you could make this available maybe to us, or this talk will be available online. So I suppose people can also find it there. So yes, I will.
Regarding references, if you check for this review article, you will find I think all the other references in there.
Brilliant, thank you.
And many more.
Perfect.
Yeah, then Stefan, so sorry, Amira, thank you very much for for moderating the questions. And Stefan, thank you so much for the excellent talk. It was really very interesting. I really enjoyed it. And I'm sure many people will download your recent review article and start studying the references and the latest developments in the field. So thank you very much also to all the participants. This is just the last talk in November. We still have 2 more coming up in December. So please don't go on holiday yet, because we need you next Monday and the Monday after next Monday. And Stefan, again, thank you so much for the talk and for being with us today from the cold Switzerland, I assume. Yeah. And yeah, and we are looking forward to stay in touch with you, and maybe next year we will ask you to update us on more recent developments. So thank you very much, Stefan, Amira, and Ilya for the backup. Yeah. Thank you very much, everyone. Have a good evening, and all try to stay safe. We don't have the vaccine yet in the pharmacies. Yeah. So thank you very much. Have a good evening. Bye-bye.
Bye.
Thank you. Bye-bye.
Bye, thank you.
Bye, Amira. Thank you very much.